Assumed that array A is used to store a heap data structure. So we are going to utilize the array from index position 1. That means we are not going to work with the index position 0. We are starting with index position 1. So the root, it will always be available at index position 1. In your implementation, you may start the index position from 0. Accordingly, you have to modify the relations. But in the nodes which we are going to follow in this course, we are assuming that the root is present at index position 1. Then if we talk about an index position I, then left child of I will always be present at index position 2 times of I. The right child of I will be present at index position 2 times of I plus 1. The parent of I will be present at index position I by 2 and its floor. Kindly note that the root of a tree will not have any parent. Then the length of the array will give me the total number of elements that can be stored in the array. Since we are utilizing this array to store a heap data structure, so there is another variable which we have to maintain termed as heap size. This heap size will tell me the total number of elements which are present in the array are actually a part of heap. It may be the case that an array element is present, but it is not a part of a heap data structure. So in such a scenario, all the elements which are present from index position 1 to index position heap size, they will form a heap, and all the elements which are present from index position heap size plus 1 to the length of the array, they are just present in the array, but they are not forming any heap data structure. So accordingly, the variable heap size, it may have a value of 0, or it may have at max a value of a length, any value in between. And since we know the heap data structure follows the nearly complete binary tree property, because of that, all the values which are present from index position n by 2 plus 1 to index position n, they are leaf elements. That means all the values which are present from index position n by 2 plus 1 to n, they will not have any children. They are actually the leaf nodes. Now we will try to verify these properties on some tree. So let's say we have this array which is being used to store a heap data structure. Therefore, we can visualize it in the form of a nearly complete binary tree, and it satisfies the properties of a nearly complete binary tree. It is a tree, it is binary, and its all levels are full except the last one. Now we have seen root should be present at index position 1. So here root is present at index position 1. Next property of the leaf nodes, that is n by 2 plus 1 to length of the array will give me the leaf nodes. Here length of the array is 10, n by 2 5 plus 1 will give me 6. So from index position 6 to index position 10, the elements which are present, they should be the leaf nodes. So if we can see, then 9, 3, 2, 4, 1. These are the values which are present from index position 6 to index position 10, and they are nothing but the leaf nodes. Then we have seen that an index position I will have its parent at index position I by 2. So if we talk about any node, let's say 2, parent of 2 should be present at 2 by 2, that is 1. So 14's parent is 16 and it is there at index position 1. If we talk about 3, its parent should be present at 3 by 2 and its floor. So 3 by 2 will give me 1.5, floor will give me 1. Similarly, if I talk about the left child and right child, then this 3, it should have its left child at 2 times of 3, that is 6. So at index position 6, I have the left child of 10. Similarly, at 2i plus 1, that is 3 to the 6 plus 1, 7th index should have a right child of 10, that is 3. So all these properties, they are satisfied. So it is a heap data structure. Next, So there is a parent node and there is a child node.